Microsoft has just announced that quantum computing will arrive 4 years ahead of schedule, and almost no one outside the company buys the explanation. In one announcement, Microsoft pulled its 2033 target forward to 2029, pointing to a breakthrough so major that it rewrote its own roadmap overnight. That should give you pause, because major tech companies don't casually cut years off a timeline unless they believe they've stumbled onto something extraordinary. But here's the part most people aren't talking about enough. The very physicists who specialize in this technology are looking at Microsoft's new chip and saying the company still hasn't proven the one thing its whole plan rests on. If that sounds contradictory, it is. And that contradiction is exactly why this story matters right now. This all revolves around a chip called Majorana 2, unveiled at Microsoft's Build Developer Conference in San Francisco. It's the second generation of Microsoft's attempt to create what's called a topological qubit, an approach to quantum computing that's fundamentally different from the methods used by companies like Google or IBM. Chetan Nayak, the physicist heading Microsoft's quantum hardware division, said the company is speeding up its roadmap thanks to what he described as rapid progress. In his own words, Microsoft has cut its timeline in half and now expects to reach a scalable, practical quantum computer by 2029. Sit with that claim for a moment. Microsoft isn't saying it made gradual progress. It's saying it discovered a shortcut so powerful that 4 years simply vanished from the calendar. If you're even a little skeptical by nature, your internal alarm should already be going off. Like and subscribe right now if claims like this raise your eyebrows, because this story only gets more interesting from here. To understand why this claim is so explosive, you need to understand exactly what Microsoft is betting on. Every quantum computer relies on qubits, the basic unit of quantum information, and qubits are famously fragile. The smallest vibration, temperature shift, or stray electromagnetic field can wipe out the delicate quantum state a qubit depends on, and that fragility is the biggest hurdle separating today's experimental machines from tomorrow's working ones. Most companies tackle this fragility by stacking on more and more qubits and using software to fix the errors that inevitably show up. Microsoft took a completely different route. It's trying to build qubits that are naturally resistant to errors at the hardware level, using an exotic particle known as a Majorana zero mode. These aren't ordinary electrons or photons. They're theoretical quasi-particles that only emerge under very specific conditions, inside ultra-cold superconducting wires, where electrons start acting collectively in ways that shield quantum information from outside interference. In theory, if you can reliably produce and control these Majorana states, you end up with a qubit naturally protected from the chaos that destroys conventional qubits. The catch is that no one anywhere has conclusively proven these Majorana zero modes actually exist in a working device. Microsoft has poured nearly 2 decades and enormous amounts of money into chasing exactly this goal, and the company's history with this specific claim is genuinely shaky. Back in 2018, Microsoft had to formally retract a paper it published in the prestigious journal Nature after outside researchers found that the evidence for Majorana particles didn't hold up under scrutiny. Then, in 2021 and again in 2025, the company faced more retractions and corrections tied to that same underlying claim. This isn't some minor technical footnote. This is a company asking the world, for a third time, to trust that it has finally solved a problem it has already gotten wrong in public, peer-reviewed science. To appreciate just how hard this challenge really is, you need to understand why almost every other major player in quantum computing steered clear of this approach entirely. Google, IBM, and most well-funded quantum startups went with superconducting qubits, or trapped ion qubits, technologies already proven to exist and already shown to work, even if they remain fragile and prone to errors. Microsoft surveyed that landscape years ago and made a contrarian wager, choosing to chase a particle that existed only on paper, in decades-old theoretical physics models, instead of building on technology everyone else already trusted. That's either visionary long-term thinking or a stubborn sunk cost trap, depending entirely on whether Majorana zero modes turn out to be real and controllable. There's no safe middle ground in this bet. Either the topological approach eventually outpaces every competitor because its qubits are inherently more stable, or Microsoft spends another decade and billions more dollars chasing a particle that may never behave the way its physicists hope. That track record is exactly why the physics community greeted Majorana 2 with caution rather than celebration. If a claim has already been walked back twice before, hit that like button, because skepticism here is earned, not handed out for free. So what actually changed with Majorana 2 that gave Microsoft enough confidence to cut its timeline in half? According to the company, the new chip swaps aluminum for lead as its superconducting material and updates the semiconductor layer using a combination of indium arsenide and indium arsenide antimonide. Microsoft says this new material stack produced a more stable topological phase, and the headline figure the company is promoting is a 1,000-fold improvement in qubit reliability compared to the first-generation Majorana chip. Specifically, Microsoft claims the qubits on Majorana 2 hold their quantum state, called parity, for an average of about 20 seconds, with some cases stretching to a full minute. Compare that to Majorana 1, where the equivalent lifetime was measured in milliseconds, and on paper this does look like a genuinely massive leap. Microsoft also revealed that artificial intelligence played a direct role in this progress through a platform called Microsoft Discovery, which uses AI agents to automate the tedious process of tuning hundreds of device parameters and measuring quantum states, work that used to take human researchers weeks to complete by hand. The company says these AI agents slashed measurement cycle times by orders of magnitude, building three-dimensional maps of device conditions that a single scientist working alone could never have produced at that speed. Researchers involved in the project say earlier attempts to automate this exact measurement process using older machine learning tools had failed outright years ago, because the pattern recognition needed to detect subtle shifts in electron behavior across billions of particles on a semiconductor wire proved too complex for those earlier tools to handle reliably. On the surface, the combination of better materials and AI-accelerated research sounds like solid grounds for optimism. But here's where the story takes its sharpest turn, and where you really need to pay attention. Outside physicists reviewing Microsoft's published data aren't disputing that the materials improved. What they're disputing is something far more fundamental, something that strikes directly at whether Microsoft has built a qubit at all. To prove a topological qubit actually works, researchers need two distinct kinds of measurements, known in the field as Z measurements and X measurements. Z measurements check the parity state of a single wire in the device. X measurements check the joint parity across both wires of the structure, and that second measurement is the one that actually proves the qubit can store and manipulate quantum information the way a real qubit must. According to independent analysis of Microsoft's new preprint, the Majorana 2 paper presents only Z measurements. The X measurements, the ones that would actually prove this is a working qubit, are simply missing from the data Microsoft released alongside its bold 2029 announcement. That's not some small detail buried in a footnote. That's the entire ballgame. Here's why that missing measurement matters far more than it might seem on the surface. A Z measurement can show whether a parity state exists and how long it lasts, which is impressive and worth publishing on its own. But a qubit isn't just a particle quietly holding a state. A qubit has to let you read information out of it and manipulate that information in a controlled way. And that's exactly what the X measurement is meant to prove. Without it, what Microsoft has technically shown is a very stable, very long-lived physical state inside a wire, not yet a device that computes anything. Interestingly, Microsoft did publish X measurement data for the earlier Majorana 1 chip in a separate preprint released back in July 2025, several months after the original Nature paper had already drawn heavy criticism. That data also failed to win over skeptics like Frolov and Legg, who argued the X measurements themselves carried interpretive problems. With Majorana 2, the newer and supposedly far more advanced chip, that same critical category of evidence is simply absent from the paper altogether, and the document explicitly describes investigating these effects as future work still to be done. If a single missing measurement could be the difference between a real breakthrough and a marketing headline, smash that like button, because this is the part of the story most coverage glossed right over. Sergei Frolov, a quantum researcher at the University of Pittsburgh, who's tracked Microsoft's Majorana claims for years, didn't hold back describing the scientific community's reaction. He said that when Microsoft comes up in physics circles these days, researchers tend to just laugh or raise their eyebrows. And he pointed out that Microsoft's earlier preprint of this kind has remained unpublished in any major journal since last summer, which he reads as a strong sign that top journals have likely turned it down. Another physicist, William Legg, who has publicly questioned Microsoft's earlier claims, goes even further, arguing the company may not have a functioning topological qubit at all, given the absence of those critical X measurements. Meanwhile, a 2025 Nature paper covering the same research came with an unusual editor's note, explicitly stating that the results in that manuscript did not represent evidence for the presence of Majorana 0 modes in the devices being studied. And yet, despite that editor's note, Microsoft's own press release at the time claimed the team had obtained exactly that evidence. Most of the nuance and caveats got completely lost in the media coverage that followed. Do you see the pattern forming here? A peer-reviewed journal attaches a formal disclaimer saying the evidence isn't there, and the company's marketing department announces a breakthrough anyway. Not every scientist is dismissing Microsoft's progress outright, and fairness demands we acknowledge that. Kartik Agarwal, a physicist at Argonne National Laboratory, reviewed the new measurement method Microsoft used to probe the non-local properties of these particles and called it fantastic progress, saying it does support the case that the company may genuinely be observing real Majorana behavior. Even some of Microsoft's harshest critics admit that the materials engineering inside Majorana 2 looks like a real, impressive achievement in its own right, regardless of whether the topological interpretation eventually holds up. Replacing aluminum with lead and achieving that thousand-fold improvement in parity lifetime isn't nothing, even to skeptics. The disagreement isn't about whether Microsoft built better hardware. The disagreement is about whether better hardware automatically means a working qubit, and on that specific question, the company and its critics remain miles apart. Microsoft itself isn't backing down from any of this scrutiny, and that confidence is worth examining closely. If you think confidence alone shouldn't be enough to justify a 4-year timeline jump, you already understand exactly why this debate refuses to die. So go ahead and hit subscribe. Chetan Nayak addressed the criticism directly in public statements, essentially arguing that physics skepticism is a normal part of pioneering work nobody else has successfully pulled off before. A Microsoft colleague named Xander pushed back even harder against critics, stating plainly that the team wouldn't be spending this kind of money on engineering if they genuinely believed the underlying physics was still uncertain. Microsoft has also pointed to its involvement in a multi-year quantum program run by DARPA, the United States Defense Research Agency, specifically designed to independently test whether utility-scale quantum designs from companies like Microsoft actually work as claimed. The company says it handed DARPA everything, including sensitive commercial material competitors never get to see, as a way of proving it has nothing to hide. Yet even that DARPA relationship hasn't satisfied outside reviewers, because the new Majorana 2 paper supporting the 2029 timeline still hasn't been peer-reviewed. Scientists who examined it for international outlets like the BBC have publicly said they want significantly more data before accepting Microsoft's framing of the result. It's worth pausing here to grasp just how much money and how many years are riding on this single scientific question being answered correctly. Microsoft doesn't disclose an exact dollar figure for its quantum research program, but industry analysts tracking corporate research spending estimate the company has poured well over $1 billion into this specific topological approach since the project began, covering specialized cleanroom facilities, custom fabrication equipment, and a dedicated team of physicists based mainly out of Santa Barbara, California. That level of sustained investment, continuing even after 2 embarrassing public retractions, tells you something important about how confident Microsoft's leadership remains internally, regardless of what outside critics are saying in scientific journals and conference halls. Confidence alone doesn't make a particle real, but it does explain why the company keeps doubling down instead of quietly walking away from a bet that has already cost it credibility once before. This is the core tension driving the entire story. A company with virtually unlimited research funding is racing to be first in a field where being first carries enormous commercial and political weight, while the scientific process meant to validate extraordinary claims moves structurally slower than a press release. Microsoft Build happens once a year. Peer review can take many months, sometimes longer, especially for a claim this contested. That mismatch in speed is exactly how a 4-year timeline acceleration can dominate headlines worldwide within hours, while the actual scientific verification needed to justify that acceleration is still sitting unfinished, months or years away. There's also a wider race underneath this specific controversy that makes the timing especially loaded right now. The United States cannot afford to lose. That framing matters because it turns a purely scientific disagreement about Z measurements and X measurements into something with national and geopolitical stakes attached. When a technology gets tied to great power competition, the pressure to announce progress quickly tends to rise, even when the underlying science would normally call for more caution and more time before any public claims get made. This pattern isn't unique to quantum computing either, and that wider context deserves a moment of your attention. Time and again in modern technology history, the gap between a press release and a peer-reviewed confirmation is where the real story actually lives. Battery breakthroughs, room temperature superconductors, and certain medical research announcements have all followed a strikingly similar arc in recent years. A bold claim generates global headlines within hours. Independent experts spend months or years quietly checking the actual data behind the curtain, and only afterward does the public find out whether the original claim survives that scrutiny intact or quietly falls apart. Quantum computing, because it combines genuinely difficult physics with enormous financial incentives and now geopolitical pressure as well, may be one of the most extreme versions of that pattern playing out anywhere in technology today. So where does this actually leave us, sitting here in the middle of 2026 watching this unfold in real time? Microsoft has released Majorana 2 to the public, and the broader platform behind its development, called Microsoft Discovery, is now generally available for outside researchers and developers through GitHub. That alone is a significant move because it means independent groups outside Microsoft will eventually have the tools to test similar approaches themselves, which could either validate or undermine Microsoft's claims faster than waiting on Microsoft's internal papers alone. The honest summary of where things stand is this. Microsoft has genuinely improved its hardware. Nobody seriously disputes that part. The materials are better, the reliability numbers are dramatically higher than the previous generation, and the AI-driven research process behind it represents a real and interesting use of intelligent systems in experimental physics. What remains unresolved, and what nobody can responsibly skip past, is whether any of that hardware improvement actually proves the existence of a working topological qubit, the single foundational claim Microsoft's entire 2029 timeline depends on. Until independent labs replicate these results, until Microsoft releases the missing X measurements critics keep asking for, and until a peer-reviewed journal puts its name behind this specific paper, the responsible position is to treat this as an exciting but unproven bet, not a settled scientific fact. That distinction matters enormously because the difference between those two things is the difference between quantum computers transforming medicine, cryptography, and material science by 2029, or this becoming yet another chapter in a string of premature announcements stretching back to 2018. What we do know for certain is that the stakes riding on getting this right or wrong have never been higher. Quantum computers powerful enough to fulfill Microsoft's promise could eventually break much of the encryption protecting the modern internet, simulate molecules well enough to speed up drug discovery in ways classical computers simply can't match, and solve optimization problems across logistics, finance, and energy that today's most powerful supercomputers currently take an impractical amount of time to even approximate. That's precisely why a 4-year acceleration claim, even a contested one, sends shockwaves through scientists, investors, and governments all at once the moment it's announced. Consider just how disruptive a working version of this technology would actually be across industries that have nothing to do with physics research at all. Pharmaceutical companies have spent decades simulating how molecules interact using classical computers, a process that often takes years and burns through enormous computing budgets just to test a handful of promising drug candidates. A sufficiently powerful quantum computer could theoretically model those same molecular interactions in a fraction of the time, potentially compressing years of lab work into weeks. Financial institutions face a similar story with portfolio optimization and risk modeling, where the sheer number of variables involved currently forces banks to rely on approximations instead of exact calculations. National governments, meanwhile, are watching this entire field through a security lens, because a quantum computer powerful enough to break current encryption standards would force a global overhaul of how sensitive data, financial transactions, and even military communications are protected. None of these outcomes hinge on whether Microsoft specifically wins this race. They hinge on whether anyone, anywhere, actually builds a fault-tolerant quantum computer at meaningful scale. And that's exactly why every claimed acceleration toward that goal draws this much scrutiny and this much attention all at once. The real catch, the one underneath every other catch in this story, is this. Microsoft isn't just racing toward a working quantum computer anymore. It's now racing to defend the credibility of its own roadmap in full public view, against a scientific community that has watched this exact company walk back similar claims not once, but twice before, and that is now demanding proof instead of promises before granting the benefit of the doubt a third time. If this story changed how you think about every confident tech announcement you scroll past without a second thought, that's exactly the point. And that's exactly why you should like this video. Subscribe for more deep dives like this one, and stick around because the next breakthrough claim, real or not, is already on its way. And you'll want someone keeping score when it lands.